So welcome to this DSCoV talk. Thanks for coming. I'm John Holland, one of the data scientists at the Center for Computation and Visualization. And I'm here today to talk about software testing. So in the first part, we'll look at why and how to organize your test cases. And we're going to look at testing a software system itself and on all of its dependencies in principle. And then in the second part, we're going to talk about how to write a comprehensive test suite. So what are good inputs and how do we evaluate correct results? What are bad inputs and how do we test those? And then how can we really be systematic in choosing our test cases and taking a lot of the effort out for you? So let's look at test organization first. Why and how we test. So maybe the first question, the deepest motivation is, why do we code? Why do we code? And the answer, I think, is because we want to answer a question correctly, which we otherwise couldn't. Maybe it takes too long to compute the result, or maybe there's some other reason we couldn't do it without using a computer. So we write code and we want to answer a question. So then what's the point of testing? In short, if you don't test, you're not going to get the correct answer. And then what's the point? So when I started at CCV, a colleague said to me, John, code is bugs. And she was right. So you're going to make mistakes when you code, but just like in an exam, you check you're working and you catch some of those mistakes before someone else does. If you don't test your code or the results and then you release them, you're at risk of some reputational damage. Maybe you have wrong data in a presentation, or you've got to retract some results from a journal. But there's really no limit on how bad the worst case can be. Software bugs in the past have led to crashed space probes, billions of dollars in losses for corporations, and deaths in some cases. So testing is important. And if you write software, it's in your interest to test it. This is really, it's on you. So testing is important, and especially testing early is really going to help you. It's going to help speed up your code development. It makes no difference in principle if you test early or you test late in the process of writing code. If you're doing a comprehensive test, you're going to do about the same amount of testing. But testing helps you catch bugs. And if you catch bugs early, you'll avoid having to recode things that you've built on top of those bugs later on. There's also a speed of development effect, which happens late in a product's life cycle, in the life cycle of your code or your analysis. If you have a bunch of tested code, which you want to modify, you want to refactor, you want to change, improve, maybe without affecting how it works, but just make it faster or cleaner, and you've got good tests of all the interfaces of that code, those are the places where you as a user touch the code, you give it inputs and you get outputs, then if you've got tests, you can just go ahead and rework the code. You can fix any bugs that you find, and if the tests continue to pass, you know that even with all the changes that you've made, it's still doing what you wanted it to do. There's another reason. Whenever we find a bug in code, or if someone else finds it for us and we fix it, we don't want to accidentally unfix it later. And by having tests which represents how bugs in your code manifested, and then check that the fix that you implemented still work, you can avoid unfixing things at a later point in time. And these tests are called regression tests, and we'll touch a little bit more on those later. So those are some reasons why you might want to test early. What about automation? So if you have automated tests of the key interfaces of your software, which you can then run with little or no effort because they're automated, then it's really easy. You can make quick improvements to code, add new features, update variable names, bug fixes, whatever, without worrying about the consequences. And if your tests start to fail, you'll know that you broke something, and then you can roll back your changes and start that change again with a little bit more knowledge about what works and what doesn't. On the other hand, if you don't have automated tests, then you've always got to remember what to test. You've got to remember what the correct answers are. And then you've got to do your manual tests for everything you change. And depending on the size and complexity of your code or your analysis, this might become totally impossible. So the takeaway is testing is on you. You should start early, and you'll get the most benefit from testing if you automate everything. So the next question is, when should we do what kind of test? Okay, before you even start coding, maybe you know what the question is that you're trying to answer, and then you can start devising what are called black box or closed box tests. This is where you work out what it is that the program has to do, work out what the specification is for its boundaries, maybe the edge cases and corner cases that you expect, or some special cases, and then work out some middle of the road cases that should always apply in your code regardless of the implementation. And we'll talk about doing this systematically in the second part of the talk. Now, once you're writing code, you can start what's called component and integration and system testing. You should also be doing regression tests for old bugs that you've already fixed. And ideally, you should always have someone else reviewing your code if you can. So if you're coding, search for a code buddy who can help you out. Maybe they can look at your code, give you pointers, spot bugs you've not seen, and you'll learn from each other. Okay, once you've got a working version of the full system, even if it's missing some of the functions that you need, you can start doing those full system tests, like usability tests or load tests or security checks. And at this point, you should also continue to do your regression tests too. And then once you're feature complete and your user tests have shown that the whole system has the right features for this release, you can continue to do full system tests of things like its stability under load or extremely high loads or over a long period of time. Once you've released your code or released your results, your users will likely tell you where the problems are, but you should really continue to monitor the system for errors, things that come up. So I talked a little bit about automation before. Component integration and regression tests, as well as your end-to-end tests, can be automated. And you might start when you're in the prototyping phase with just some manual tests on a function on the command line or in a notebook, or some other kind of test that you're doing whilst you're building the code. But if you're writing software for use over a long period of time, you'll really quickly want to automate those tests. So you can start by putting them into a script, which you can run with a test framework. In Python, you might use PyTest or unit test. In other languages, there are other test frameworks. Just look for the one that applies for your language and just get going. Once you've got those tests and you've put them into a script or some other way of running them, you can automate the running of them. If they're extremely quick, it can be valuable to have them run every time you commit some code to your code repository, to your version control system. And if they take longer, you might want to run these just before you merge a branch of your work. So if you're using pull requests on GitHub, really helpful for the code review, that's something that you can automate. And this approach of automation and running these tests automatically means that you're much less likely to commit any errors in your code base, any bugs, even in the first place. So you're just not going to have those bugs in the future. And just as an aside, if you're not using version control for your code, you really, really should be. I did a talk on that last year, and the link is here to the notes. So if you're interested, go and have a look at that. All right, so let's have a look at the testing that you might do in these early phases of development, the unit component integration and regression tests. Okay, we tend to organize tests hierarchically, and we're going to start today at the bottom. Now, the terms component and unit tests, you'll often find these treated as synonyms in the literature. I don't think the names per se are really important, but there is a distinction that some authors draw, which we might want to think about and which might give you a better handle on what authors might be getting at. So in my interpretation for today, unit tests test very small pieces of code in strict isolation from anything else. And that strict isolation is the key. Component tests are similar to unit tests. They might test the same thing, but we don't enforce that same isolation requirement. Isolation means that if your code uses another function, then you might make that function that your code is calling into something that you know is always guaranteed to give you a result that you expect. It's called mocking. But this is really, really tricky to get right. Often you'll find yourself mocking something, you'll make the mock wrong, and then your code will be wrong because the thing that's underlying it that you're trying to mock is actually implemented differently and actually works in a different way. So my recommendation would be that component tests will probably do, and you'll probably need more component tests than any of the other kinds. So start there. Once we have those components, we can start integrating those into larger and larger pieces. And these are called integration tests. And what we do is we see how they interact as we've built them together, and we test larger and larger pieces of code. The highest level of integration is that of the full system, and that includes what are called end-to-end tests. And this is where we get the most value from our tests. These are those test cases which are the most similar to the behavior that a user might see or care about. But these tests are often also the hardest to write, and you're likely to have the fewest of them. At this point, I'd just like to point out that the boundaries between units, components, modules, subsystems, and the whole system are often very unclearly defined. So in my reading, everything from the component test to the full system test can be seen as a kind of integration test. So we shouldn't get hung up on the nomenclature here. So why do we build these things up? So if you're smart about how you build and test your components on the lowest level, the idea is that you're going to have enough confidence in the components and the modules to safely make assumptions about them so that the next level up in the testing hierarchy, you can make those tests simpler. And a corresponding idea is if you find that you're doing the same tests or testing the same things at every level in your testing hierarchy, then you might be doing these tests wrong. You might want to simplify some things, push those tests down to the lower level, and then make more assumptions just so that you're not running too many tests. Okay, so that's the bottom-up approach, how we integrate things together and test them. But there's also the idea that you might go from the top down. So if you've got an existing system that you're coming to test, which doesn't have any tests at all, then you may well start the other way around. You might start by doing a system test and check that the whole thing appears to be doing approximately the right thing, and then work down through the components and units to check their specific behavior. For a really complicated system, this is likely to be complicated too. You might have a hard time identifying the boundaries in the special cases, and you'll be less sure when bugs arise where they're coming from. But that's better than having no testing at all, and it might give you a good feeling for what the whole system is doing. So the important thing here, the important thing for this whole slide is the real value comes at the highest level. You actually really care about whether the full system works, so that's what you should be testing. But tests at these lower levels can help simplify those tests of the system. So that's system tests. But to be absolutely certain about the functioning of your program, well, this is really impossible because your system is dependent on a whole host of other things, what we call dependencies, which in principle you also need to test. And they include going from our system sort of down. Let's start with the runtime environment. That's what you're running your program in. If you're running in something like Python that isn't compiled, you're going to be looking at the language version that you're running in, the Python version, any modules you've installed or any modules imported. And in principle, every statement and function and class and method that you're using from those modules. Then you might have the operating system and its state. So whether you're outputting things to the command line or a graphical user interface or writing to the file system, it depends very much on what the state of those things were before you started your test as to how they react. And that date might be really important. Then you've got the operating system itself, whether you're running on Windows or Mac or Linux, and what version that you're running on. And then maybe whether the operating system itself is virtualized or in some container or virtual machine, or maybe it's running on bare metal. And then you've got the platform that you're running on. What about the processor architecture? Maybe one processor architecture works in a slightly different way, or maybe the firmware on your computer is different. Maybe it's translating commands from the operating system or to other programs into the commands for the hardware, including the CPU itself. And this firmware might have bugs in it too. And then you've got the particular hardware. How long has your machine been running? Is its memory full, or the main storage? Or has it just been hit by a cosmic ray and a bit in the memory has been flipped? The same applies in any of the other connected systems that you might have. So maybe they have shared memory, or maybe there are network connections between them that we need to think about. And then you're also dependent on the world, what time of day it is, and which time zone your system and the other systems are in. Or what's your location on the globe? Do you have transmission time delays in the network? And whether maybe you're in a solar storm and all the network connections are a little bit iffy right now. And then you've also got those people. People are really tricky sometimes. Is one person's authentication token required for the software to work? Is there documentation to fix the software if person X isn't there? Maybe the only person who knows what some related system is doing has left the organization. And maybe the organization itself has forgotten what system Y does, if anything, and so on. These dependencies go all the way down. Bugs really can be in any of these places, and in principle, your program could be affected by them all. And what I'm trying to say is that you can only do so much. So if that means you're going to do some tests under reasonable circumstances and not worry about the external factors, that's fine. But you really should be aware of the limitations of your testing and in what circumstances things might go wrong. Another important idea is that you know about those limitations and program in such a way that your code is easy to test. So try to avoid depending on things which might be unknown, like a particular path on the file system or the state of the graphical user interface or the command line. This can't always be done, but if you limit your program, your code's exposure to these things, then you reduce the risk of bugs cropping up. And another thing to think about is try to use dependencies that are well tested themselves and known to be relatively bug-free. This means using up-to-date versions of mature software that's not necessarily the latest and greatest bleeding edge version for all of your production work. And it also means testing the latest and greatest bleeding edge versions and dependencies early to see if they show new bugs or fix bugs that you didn't notice before. NASA famously were able to prove mathematically that their 500,000 lines of code for the space shuttle were bug-free for all conceivable inputs. That meant it would do the right thing. You are unlikely to need that level of confidence, so yeah, just roll with it. So that's test organization, very briefly. Let's have a look at how we write a test suite for a single system or program systematically. Now, the key idea with testing is that our program, that's the thing in the middle, takes some inputs and transforms them into outputs. And we want to know that for all the conceivable inputs, the outputs are correct. Either we get the correct results or we get the correct errors, exceptions. And we also want to be reasonably certain that it's not doing something additional, like, I don't know, writing extra files to your hard drive or sending me all of your Bitcoin. Although if you'd like to build that into your software, I'd be happy. So let's look at the outputs first. They're really key. What does it mean for a function's output to be good? And there are several criteria that we can apply one after the other, and they really build on top of each other. So the first question is, does your function return something when it should return something, or did it return nothing? That's one check to do. Then, is the thing that your function returns the correct type, or is it the wrong type? Then maybe, is it in the right range? And this might also include cases where you know that the sum of some values needs to be invariant, even if you don't know the precise values. Say the sum of probabilities from some group of functions should be 1. Then you can ask the question, all right, is it close to the correct value that I know? And then is it really identical to the correct value? Is it spot on? And these are all the levels of correctness that you might want to check. Of course, you can jump straight to the spot on criterion if you know it, but a lot of the time you won't. And these plausibility checks that get you closer and closer to the correct result might be the best that you can do. This kind of approach also applies to exceptions we might expect. So when your program throws an error without crashing, you could check for the existence of an exception and whether it's the correct type, and if it has a value or result associated with it. Perhaps there's some error message that you should get back, and check whether that's absolutely correct. So in my experience, I usually just check that my function raises the correct type of exception, because the precise value is often some implementation detail. And your exceptions might be different. You might know exactly how they should look, and it might be important that they look exactly the right way. But this is something to think about. And I'll point out here that sometimes your tools are going to guarantee that some of these things are true. For instance, your compiler might check the types of some outputs if you're writing compiled code. So you don't necessarily need to check that yourself. But in my world, I use Python and JavaScript a lot. Expecting an integer and getting back a poem or something is a real risk. So that was outputs. Let's look at inputs. And this is where we really need to work out what inputs to test. And this is really complicated. So let's start by looking at all the conceivable inputs for any program that you might like. There are 3 classes of inputs that I'd like to look at the very start. The first are good inputs. These are data we expect. Maybe the function is a function that accepts numbers, and then anything that fits into that class of number would be a good input. Then we have bad inputs. If we give the function the wrong type of thing, like it's expecting a number and we give it a cat or a poem, and it doesn't know what to do with that, that's a bad input. And then we've also got the empty inputs. So for some functions, empty data might be good, or they might be valid, or they might be bad or invalid. And we need to think about all of these things. Now let's look within the valid inputs. We have a few different cases that you might want to test. So the first is the nominal, middle of the road cases. These are the ones that you're most likely to meet in your usual course of work. And these are also called happy path cases. Some parameters that you have are going to have boundaries within their valid ranges, or discontinuities where the behavior of your function or your program changes. We've got these internal boundaries. We've got compound boundaries where 2 boundaries meet. We've got edge cases, which are boundaries at the very limits of what is good. And we've got corner cases where 2 edge cases meet. And we might have some special cases. Perhaps there are single values which have some special meaning and are rare, but are really still fundamental to the behavior of the function. And we need to cover all of these cases when we're looking at good inputs. But comprehensive testing means checking that for all conceivable inputs, good and bad, defined or empty, the function does the right thing. So we also need to think about these bad inputs. And actually, we'll see later, there are many more bad inputs than there are good inputs. So you might end up having many more bad tests than good ones. And what does it mean to do comprehensive testing? So comprehensive testing means that checking for all conceivable inputs, good and bad, defined or empty, the function does the right thing. It's either going to return correct results for valid inputs, or it's going to fail as expected for invalid data. We've got to start testing somewhere. So where do we start? We start with a single nominal case test, a single happy path test. This is going to be the thing that helps us ensure that the code is returning the correct types. It's giving some plausible output for a single case. However, a single nominal case isn't going to be enough to be sure that your function is really generalizable to the full range of valid inputs. So as a minimum, you need to test nominal cases in every region of the input space. That's all the different regions separated by boundaries. This is potentially really onerous if you have more than a couple of input parameters and lots of boundaries. So later we'll look at techniques that you can use to help out with this. You also need to identify every special case which behaves differently to your nominal cases or needs some kind of special handling. Now, you might be able to guess some of these cases before starting, like maybe you have zeros or empty strings or values with special meanings or nulls, or you might discover them by accident. We need to keep all of these special cases in mind. But we can do better than that. Ideally, if you can, you really should be generating a large number of representative nominal cases for the whole range of valid inputs. So if you're able to construct known inputs and outputs and test that those come out right, then do that. This is also potentially really tricky and very time consuming, but there's a technique called property-based testing that will help you automate this. There are some property-based testing libraries are available for a bunch of languages. Just check out the bibliography at the end of this talk for more info on these. And if you're doing property-based testing, you might discover some special cases, you might discover some bugs, and those will help you identify those special values. This might be the best possible case that you can do with your code. If you have too many potential values, then you just can't test them all. So you might have to stop here if you don't want to go as far as the NASA folks did and get formal proofs of the program that you've written. Okay, so that's nominal middle of the road cases and the special cases. What about our boundaries? So these need special treatment, but it's pretty simple. Fundamentally, the approach is to test just below, precisely on, and just above each boundary. And we're going to make an analogous set of tests around compound boundaries. So precisely on the compound boundary, then just above or below in all the different directions. And the same applies to our edge and our corner cases, where we're going to check that the behavior when we're inside the edge, on and outside each edge or corner is correct. And at this point, we're going to be dealing with bad tests outside the corners. And we need to know that the code is going to throw us errors in just the right way. So that's boundaries, compound boundaries, edge and corner cases. One thing that we've got to deal with a lot are collections. So collections are things like lists, arrays, or mappings. And these contain other objects. Maybe you have a string, which is a collection of characters, or a list, which could be a collection of anything. A mapping, a dictionary, could be a mapping between strings and any different kinds of values. You might be working in a language that's got structs or data classes, or you might be using a database. All these things I would call collections for the purposes of this talk. And we need to treat those on both axes that we have. So the first axis is the data volume, how many things that we're putting into our collection. And the other thing is, what are the range of values that are acceptable for to put in each of our collections. So let's start with the data volumes. We should be testing for the full range of data volumes. So you'll have your nominal cases. You'll already have those from your happy path analysis. But then you might want to look at the minimum amount of data. Maybe your collection is an array, and a valid input is 0 elements in that array. So you need to check for that. You also need to check for the maximum case. Maybe your data set doesn't have an upper limit on the size. Maybe it's a Python string that I think it was 9,000 terabytes was the longest possible Python string. You're unlikely to have a string that long to test, but you'll have to pick something reasonable for your use case. Maybe it's a really long string that you'd never expect to see in the wild, or maybe you've got an employee database. Maybe you've got 10 times the number of current employees in your organization that you test. And then we're going to look at those cases way outside. So what happens if we just give it too much data? Is it going to crash the whole computer? Is it going to cause things to be corrupted? We don't want that. So we want to test those extreme cases. And the same on the too little side. If there is some minimum amount and you give it too little data, maybe you need an array with at least one value to make any sense, and maybe you give it 0 values. You want to see that it's going to crash in the right way. Okay, so we've looked at the data volume. What about the full range of valid values? So for each of those tests that we just talked about, from the smallest to the largest, you also need to look at what the data values are that you're putting in. So let's start with the minimum case. So maybe you've got 0 values that you're putting into your collection, then it's just going to be empty. There's nothing to test here. But if you're putting 1 value into your collection, maybe you've got a number that you're putting in. Maybe you put the lowest possible value for that number and some middle of the road value for that number, but also the highest possible value for that number, just to make sure that the behavior works for all the range. And then maybe we've got some larger data set that we're putting in, and we're going to do the same again. So we're going to put lots of the smallest number, lots of the middle number, and lots of the largest possible number. And then we're going to do the same with ranges of values. So lots of low values, lots of medium values, lots of high values, and then across the whole range. And then later on, when we're looking at the maximum case, we're going to do the same thing again. So we're testing all the different sizes of inputs with all the different values that we might have. And the things that you might want to think about here are, what are the values? What are the possible values for my particular data type? So maybe you're dealing with strings. So maybe you deal with just the simplest strings, the ones that you'd see often in English, the ASCII characters. But maybe you want to think about putting all of your Unicode characters into your string, maybe including those weird things like the character that flips the direction of the text from left to right to left, and then having a few of those, or null characters, or characters that get composed together. These are all things that you might want to think about. What about with numbers? If you're dealing with signed 64-bit integers, then you're going to be looking at numbers from -2 to the 63 to +2 to the 63. So you might want to think about all of those. And then maybe we're thinking about this employee database again. Maybe the salaries are going to go from 0 to 10 times the highest possible salary, and everywhere in between, just to see that your collection and all the code underneath it still works. Yeah, so that's collections. So we've got just normal values, and then we've got collections. What about our weird cases? What about the bad data? And I mentioned at the start that there are many more bad cases than good cases. It's sometimes really tricky to work out what these are. But having a list like this might help you. So we're trying to find places where we hadn't realized that software is going to break, rather than showing that it just works in those cases that we already know about. And one of the things that really can trip us up is making assumptions when building software. Often those assumptions aren't going to be shared by other people who are using your code. So the first thing is you should really check your assumptions when you're writing code, and write many more tests which break those assumptions if you can work them out. And this is one great way just to be sure that the code won't seem to work when actually it should be throwing an error or producing, or actually it's just producing incorrect results. You should work out what is possible to represent with the data type that you're using, and compare that to the cases that you actually handle. And if there's a gap, you can create tests to fill that gap. And if you're using a different data type to one of the ones listed here, you could look for analogous cases to the ones for your particular data type. So let's have a look at this fairly incomplete list. If you're dealing with Booleans, you're expecting true or false values, maybe you give it a none. or an unexpected combination of Booleans. Maybe you always expect 2 trues and then a false, or the other way around, but maybe give it a weird combination. And if that doesn't work in the right way, maybe you need to modify your code. What about numbers? Zeros and nulls are really weird. Like, you can't divide by 0. If your code does division, then you're going to have to check what happens if someone puts in a 0. What about infinities? We can sometimes represent infinities, and they might have weird behavior too, just like not a number values or negative values, or maybe complex values. And then maybe your users are doing weird things, like your code is expecting an integer and they put it in as a float, or maybe they like fractions, or maybe they give it an array of a single value rather than just the value itself. And maybe they're going to give you a string representation. Maybe they're going to write out 1, 2, 3, 4, 5 in a string and expect that your code deals with that. What about strings? So strings, we use strings all the time. These can also be nulls or nones, or they could be empty strings. They're slightly different. Then you might have these values at the very, we talked about ASCII already. And what about spelling mistakes? What if you're expecting a particular spelling of a word, you get something else? Or those control characters? What about invisible characters like non-breaking spaces or accents? If you're dealing with strings in a database, then you really need to be thinking about injection attacks, whether or not someone would be able to put a query into one of the text strings that you're expecting that will corrupt your database or extract data that they shouldn't be able to see. What about if you're expecting email addresses and you get something that's got spaces in it, or a weird URL or a weird host name? And then things like names. Names are really complicated. So if your code is expecting to get first name, last name, but the person that you're speaking to or working with uses last name, the family name and the given name in a different order, then that's something that you'll want to think about. Dates and times are a real nightmare. So month, day, year, in my opinion, it's crazy, but it happens all the time. Day, month, year isn't much better. I think using the international standard year, month, day with dashes in between is excellent in code. You should totally do that. Also use years that have 4 numbers in them rather than just 2. And time zones, good grief. Don't talk about time zones. You've really got to think about time zones. They're a nightmare. Arrays. So no rows, 1 rows. What about 1 column rather than a different number of columns? Dimensions. It just goes on and on and on. I don't need to go through all of these. Is there anything in there that's particularly interesting? No, I think you get the idea. So another way to find bad examples is by writing regression tests, which we talked about a little bit before. So often you're going to discover bad examples just by accident. Then you're going to fix the underlying bugs, but you can leave those tests in the test suite for the future. It's a great way to find those bad examples. All right, we've looked at all the different ways to produce tests just of a black box, a closed box that we can't see inside, where you can really see what the parameters of a function are that it should accept and what the correct answer is. And as I said at the start, you can write these tests without even having working code. And in principle, you should be able to catch every boundary case and specify every exception that the code should raise if it's got a really good specification. This probably isn't going to be the case if you're writing software for research, because things change all the time. But in principle, this might be possible. But once written, the code might do all of the things that you've told it to, but it might still be wrong. Perhaps there's some additional special case that you've written into the code, but it shouldn't be there, but it wasn't caught by any of your test cases. Or the code has some weird side effects you weren't expecting, like writing extra data to disk or sending a report to some cloud service that the user doesn't care about. Or maybe the code works perfectly the first n times you run it, and you only run it n times in your closed box tests, but then it does something wrong on the n plus 1th time. So one way to find these errors of commission, these are things that you've written in, is just to inspect the code. And these are called glass box or white box tests, where you give the code some input and you can follow exactly what it is that it's doing. To be really confident in your software, you need to have both black and clear box tests, glass box tests. You need to be able to see both sides. And what can we do with these glass box tests? So code reviews are one kind. You might use something like a spell checker or a linter that's going to check your code, check that it's conforming to style guides. They can be a useful thing because you can avoid building in bugs that are just to do with the way that you've typed something. You might have type checking that's checking whether or not you're giving it an integer when it's expecting a float or vice versa. You might also have duplicated code. So duplicated code is tricky because it might work right now, but later on you change one copy of it, but you forget to change the others, and then your code might break. And static testing checking can help you find this duplicated code. Or you might have code in there that in principle is impossible to reach right now, but you might accidentally include that in a process later on, and it's not been tested. So we want to be able to check that we're testing everything. There are some techniques that you might be interested in. So structural testing or basis testing or structured basis testing is a way of going through your code, stepping through it, and just checking that every line of code is covered by a test case. Equivalence partitioning is related but different. So let's say you've got a gazillion tests, but actually they're all testing the same thing, just in lots of different ways. Equivalence partitioning is a procedure where you can check that you're not doing too many tests for a particular thing. And this is in direct conflict with what I said earlier, which is you should test many, many different things in your code. You should have lots of tests of normal middle of the road cases. Some people say using equivalence partitioning, you should reduce the size of your test suite and just test the minimum. I think that's a judgment call for you. I just wanted to point out that that exists as a technique. Okay, and then, so we've looked at the internal behavior, just in terms of the code. We can also watch how it runs. So we can load our code in a debugger, and we can step through it, and we can run what are called coverage tests. So we can run our test suite within the framework of, we run a test suite, and the coverage tests go through and they check that every single line of code is evaluated. And if you do what's called branch testing, that checks that every single variant of an if statement, so every true or false predicate of a logical statement, that all the options are going to get covered, and your code goes every route through, every route through your code gets tested in your test suite. All right, so that's an overview of our black box and white box testing. We've got a few more minutes. So I'm just going to summarize. In the first part, we looked at how to organize test cases of the system itself with unit tests, component tests, integration tests, and system tests, and then looking at its dependencies, thinking about runtime environments, operating system, the platform, and the hardware, and of any other related systems. The important thing about testing from the first part is it's on you, and you should really start early. And if you get the chance, automate those tests. And in the second part, we've talked a little bit about how to write a comprehensive test suite. So we've looked at good inputs and their correct results, and bad inputs and the expected ways that they raise exceptions, and how to identify test cases like middle of the road, boundaries, edge corner cases, and those special cases. At this point, I'm just going to point out this repository. I'm going to open it up. I'm going to try to open it up. Can I open this? One second. So if you are interested in seeing all of this that we've talked through very theoretically applied in the case of Python, there's this notebook that's linked as part of this repository, which goes through writing a comprehensive test suite for the greatest common divisor function. So that's the function that takes in two integers and works out what the largest number is that divides them both with no remainder. And in here, I'm just going to point out a couple of things. So I mentioned property-based testing. I think that's particularly interesting here. A lot of tests. You should be able to download this, install it, and run it if you like. So here's the thing. Property-based testing. The technique called property-based testing says, all right, you've got one test case. Can we build lots of test cases that test the same kind of thing? So let's say you've got your GCD function. This is our GCD function. It's going to take in two values. In this case, they're called A and B. And it's going to return you the greatest common divisor between the two of them. And in this test, what I'm doing is I'm saying, give me two integers of any size, using this hypothesis. Give me two integers of any size, and I'm going to test some facts about what this GCD function should do with two integers of any size. So we're looking for invariants that apply always, and we're going to test those. So we're going to say, right, I've got two integers, but I'm going to assume that they're between 0 and 4 million. That's just a limitation because otherwise the computation takes too long. We're going to calculate the greatest common divisor of these two, and then we're going to do our checks. So is the result an int? Is an integer? Is the result greater than 0? That's a fact that we know. That's the range limitation. What about, is the result the same when we swap the values around? And then we can run those tests. And what this hypothesis module does is it just throws in a bunch of different integers and just checks all the values. And it does this really quickly, and it's great if you get bored writing test cases. I also said earlier, if you've got a way to construct true results, and here I'm just putting together a way to construct true results, then you can run those tests too. So we're doing the same thing. In this case, to construct the correct results, we need to give it some lists of primes that may or may not have some common elements. And then we're just going to check that the values that we get out are correct for all of the values that we can think of. So if you have, let's look for some non-trivial examples that it managed to put together. I don't see any. So here's one. These two numbers are the product of primes, and we've been able to construct that this is the true value just based on the multiplication, and our result from running the function is the correct one. So if you're interested, take a look, and if this is something that you'd like to implement for whatever code it is that you're using or you're writing, and you don't you can't quite get it just from this, then come along to office hours and we'll try to help you out. Send me a message before and I'll try to be there. Yeah. Was there anything else in here? yeah, I think that's it. I think we're gonna pause there, and I would like to ask if you've got any questions. Thank you. So no questions on the Zoom. George.
I guess, is there any guidance on prioritization strategies? Because I guess you can spend weeks describing all the test items on certain limitations, like where to start, given constraints.
So I think from my perspective, if you've really got constrained time, then you should start here at the top if you can. So start with the whole of the system and make sure that it's working in a reasonable way. You're not going to be able to be completely comprehensive with that, probably, but that is better than nothing. And you get the most value when you test up here. That means that you're making assumptions all the way down. That means that you're assuming that that anything that you don't test on lower levels or that comes from lower levels just isn't going to be tested. You're very much dependent on the runtime environment. So in that case, it'd probably be best to say this software, the system was tested on a particular version of Python or JavaScript or whatever on this operating system using this platform and with a description of the hardware, just so that people who are using that can understand and know what the limitations of the testing were. I think that would be the key. And then if you find that you've got more time, you can always go one level down, or you can test the same thing but on multiple platforms, and start building up that way. I think that's what I'd go for. Any other comments on that? Questions? Go ahead. What fraction of your time should you be spending on coding, on testing? I don't know. Any ideas? The last week I've spent writing tests on one of my projects, which was probably too little. It was probably 1% of the lifetime of the project. So I think that's too little, and I think we would have benefited from many more tests. One thing that you can do is so you might be aware of test-driven development, where the first thing that you do is you write a test, and then you write the function, and then you extend the test and you improve the function to do the extra thing that you're testing. And I think in that situation, the boundary between testing and coding gets a little bit difficult to define. You're probably going to end up spending, I don't know, 30, 50% of your time writing tests. Maybe it's even more than that. Maybe writing 75% of the time just your tests and making sure that they work. Maybe that's what you should be aiming for. I don't know. Any comments on that from Brad? Go for it.
As you move forward and you add more custom things.
So just to summarize, if you start testing at the beginning, you'll probably have some larger effort that you need at the start of your project, just to set up the framework for the testing. But over time, that testing will become quicker, and you'll spend less time building that framework and writing those tests because the structure will already be there. All right. Any other questions, comments, ideas? If not, then I'll say thank you very much for coming. I really appreciate your time. And yeah, hope to see you again some other time.